Good morning. As already pointed out, the topic of my presentation is photonic front-end technologies for Terahertz communications. And I'm here from the University of Duisburg-Essen, working at the Center of Semiconductor Technology and Optoelectronics. And before I, go into the details, I just have to say a few words on the acknowledgement. So the work I'm going to present here is funded not just only by the Terahertz network, but also by other resources from the local ministry, from DFG, from the German ministry, and also from the European Commission. So a couple of work was supported by these funding organizations. I'm located here in Duisburg at the Center of Semiconductor and Technologies and Optoelectronics. You see a picture here of this building, and you see that we have the clean room facilities here on the right hand side, and in the left hand side we are using the offices and also the labs. So this is basically where we are doing the technologies. We are making the chips and integrating the chips, packaging the chips. So today I will walk you through, photonic RF front-end technology. I will explain you how they are working, what is the function of a photonic front end, what are the components that are required to fabricate such a front end, and we will then go basically by key components. We'll have a look at all the key components required to do this kind of front ends. I will mostly address these higher frequencies, and I will show you a couple of applications that we are undertaking with this technology. But let me start with the first slide, very easy slide, generic advantages of Terahertz Photonics. First, explaining what is a photonic front end. Basically, you see here an example that could be for wireless communications. We have an antenna with a wireless radiation, and then we have an optical fiber, and the interface between the optical fiber and the wireless domain is then the photonic front end. That is one easy example explaining the technology we are going to talk about today. So what are the advantages of using photonics for these kind of technologies or front ends, and why are we using them at high frequencies? There are a couple of advantages. I listed a few here, and I'm going through them. The high bandwidth is what we will be talking most about today when we talk about communications. The key advantage of using photonics and terahertz is the high bandwidth that we can provide. We will talk a little bit about low loss, because we can send even high frequency signals over fiber at almost zero loss. This is completely different to cables. So even when we send a terahertz signal, we are only having a very low loss when we use optical fiber. We have a low EMI. We will not touch it in detail today, but it is an advantage of using photonics. Also, the other advantage of using low weight. High frequency, which means that we are transparent compared to optical frequency, is an advantage, for example, mainly for imaging. We can look through closes using these frequencies. Not so much of an importance here for the communications, but we will touch it a little bit. Small wavelengths, we have a little smaller wavelengths than at microwave frequencies. That allows us to do imaging, for example, at much higher resolution. And we will also touch this today in the presentation. Okay, going as a motivation slide into more details in terms of applications. So I listed some potential applications here on the left-hand side. I started with some communication applications like fixed wireless access, mobile 6G communications, satellite communications, also Earth observation, radar imaging, time synchronization, and automation. It's just a few applications that we can tackle with this technology, and I'm going to present you examples for all of these applications during my talk. We have here two streams. On the one hand, the use cases, on the other hand, technology. We are building technology to enable new use cases, but also to achieve better performance of existing use cases. And the work that I'm going to present today will focus mainly in the frequency range. You see this in the lower right figure here. We will target frequencies, mostly the terahertz range. Some results will have operation frequencies at lower frequencies. So let's say everything between 30 gigahertz and 300 or higher frequencies is what we will be talking about today. All right, so that's for the introduction and motivation. So I will have the following outline. I'll tell you first what is the generic architecture of a photonic terahertz front end. And then we will go into details, showing you examples for front ends that are used for wireless communications and front ends that are used for satellite communications. And then in the last section, I will also show you some other examples for other applications, for example, spectroscopy and imaging. We'll have a couple of videos during my presentation, so it's not just slides. We'll also show you some of the applications in real life, at least in a video. All right, so starting with a very simple slide here is to explain what is the function of this front end and what are the key components required to build it. So on that slide, on the left-hand side, you have the optical fiber. On the right-hand side, you have the wireless domain. And in between is the photonic terahertz front end that operates in full duplex, so in both directions. And if you go for, let's say, the downlink from the fiber to the wireless, you may have an optical beamforming network. We will talk about this, that is necessary to steer the wireless beam. And you have an opto-to-electric converter. I just named it here OE. And then in the other direction, we call it the uplink from the wireless to the fiber. We have the receiving antenna, and then we have to convert the electrical signal to the optical domain. So we have an EO component. Again, we may have an optical beamforming network and then go on fiber. So this is the key function of the photonic architecture as a general overview. And in the next slides, we will talk about how are we going to build the OE components, and how are we going to build the electro-optical converters, and also we will have a look on how to make optical beamforming and how to use it for different applications. Let's go first on downlink. So we're now talking again for fiber to wireless, and we need this optoelectronic component. Maybe most of you know how to do this, but I try to explain you how we can introduce data from the optical domain and convert it to electrical domain, in our case to a very high frequency, terahertz frequency, and then radiate it by an antenna using a wireless channel. So this is the next slide. It explains you how we do in general this conversion from optical domain to RF. So this is a very easy concept that we are using. It's an optical coherent system. It consists of two laser diodes that you can see here, a modulator and a balanced photodiode. And at the output here on the right-hand side, you have the current, which we want to use in order to radiate it by an antenna. So we may have an amplifier after this balanced photodiode and antenna. So how is it working? Very briefly explained, we use a laser operating at a continuous wave, and that is shown here in this diagram. So we see amplitude of optical frequency. This laser may have 200 terahertz frequency operating at 1.5 microns. It's unmodulated, so it's a very low line width, and we see this in the diagram. Then we use a data signal. This is electrical domain. We have basically a baseband signal here that you see here in blue, which is used in order to modulate the optical carrier. So after the modulator, we have the optical carrier and the sideband, which is basically both sidebands which are carrying the data that we are modulating onto the optical carrier. Now what we do is we superimpose another laser, and this other laser is operating at a different color, if you like, a different frequency than the first laser. So you see the dashed line here is maybe the old laser, and the new laser here for LO is operating at a slightly different frequency or wavelengths, and the difference frequency between the two is the desired RF frequency. If we put all of this into this balanced photodiode, then we are generating an electrical signal that is oscillating at the radio frequency RF. It can be terahertz, and it contains the data that we are using to modulate our modulator. So this is the concept, and in order to do this, we need lasers, we need photodiodes, we need modulators, and I will now walk you through some of these key components in order to understand the generic operational principle and to see the advantages. I will start with the photodiodes here. They are most critical because if we want to use that at very high frequencies, we have to have photodiodes that are operating at very high frequencies, and there are just a few organizations worldwide that are able to do this. So this shows you one of the photodiode chips that have been fabricated here in our department, so using our clean room facilities. We call it MUTC, photodiode, modified unitraveling carrier photodiode. And the challenge is to achieve a very high output power. And here you see, for example, this is the output power as a function of the photocurrent, basically as a function of the optical light intensity. And we see we can reach here several milliwatt of output power from a single die. The next question is, of course, to what frequencies can we use it? The top right figure shows you the output power as a function of the optical intensity or photocurrent. And you see the dashed line here is the quantum limit. So that's the perfect operation. And you see for the lower frequencies like 30 gigahertz, we are very close to the quantum limit. For higher frequencies like terahertz, we have a little bit of loss, but still we can reach milliwatt output power level even at 300 gigahertz from a single die. And the lower right figure shows you the frequency response of one of these photodiodes. They typically have a 3 dB cutoff frequencies in the range between 100 and 150 gigahertz. So when we operate at 300, we are using them beyond 3 dB cutoff, and we are only interested to achieve maximum output power by modifying the layer structure and modifying thermal dissipation in order to reach high output power levels. So that's one of the key components to transfer the optical signal to terahertz. If we want to do that in a system, we kind of have to package it. We cannot use the chip. So we have to integrate the chip with antennas, and that have to be then integrated into a package, for example, a package with a rectangular waveguide. So what you see here on the top left is the chip. The photodiode you cannot see anymore because it's so small. It's basically between the gray passive optical waveguide, POW, and the yellow metallic structure for the antenna. So the photodiode sits actually between the gray and the yellow area here. And what you see here is everything which is required in order to radiate the generated output signal to a rectangular waveguide. It also contains filter structures for the biasing of the photodiode and some other functions. You see on the right-hand side the performance of this antenna over a certain frequency range, and you see we can cover a huge frequency range. Here, this is even more than a full band. A full band for the WR3 would be 220 up to 320, and here we are even wider than the full waveguide band. You see the transmission loss is quite low. This is the blue line, and the red line is the reflection loss. You see for the WR3.2 waveguide, we have a very low reflection loss. It's lower than -10 dB, so the input reflection is very low. Then we have to place the chip inside a package, and that's what we have been doing in collaboration with startup companies from our own institution, also funded by the national government. Here you see a package device here on the left-hand side. So the optical fiber is coming in. You see a DC connector here, and then the terahertz output here is a WR3 hollow waveguide. It's this small aperture that you can see here in the left picture, and this is where the terahertz radiation basically comes out. And the optical signal comes in via the optical fiber. And on the right-hand side, you see the performance. This is for a medium photocurrent of only 10 milliampere. We are reaching something between -10 to -15 dBm output power. We can operate these photodiode chips up to 30 milliamps, so at much higher photocurrent levels, so the output power can be increased. The maximum saturation output power is in the area of about half a milliwatt at around 300 gigahertz. So that's one fundamental component. Can we further increase the output power? Here we can. We have developed here these kind of power combiners. So this is basically free space power combined the output power from a single die. In that case, for example, we are using 4 dies. And then we have a structure here is this hollow waveguide structure, which combines the output power of 4 chips. And on the right-hand side, you see the performance of this package here. If it would be perfect package with no loss, you would have 4 times the output power because we are using 4 chips. We are reaching something like 3.5 times the output power over the full WR3 band. So almost the perfect power combining here. And that means we can have much higher power if we are using this kind of technology and using free space power combining in these waveguide blocks. All right, the next step is then the other direction. We need to receive the terahertz signal, and that means we have to down convert it again to a frequency that we can use to measure the data again. So now we are looking on the uplink. How can we down convert the received terahertz signal to IF frequency? We are using usually mixers, but this is completely independent. If we want to do it coherently, meaning that we are locking it now to the transmission to make it more sensitive, we would have to use a new component which we call an optically pumped mixer. In the past, this wasn't possible. The reason is that these mixers in the terahertz domain require a local oscillator power that could not be provided by photodiodes because the photodiode output power was too low. So what you see on the left-hand side is the red bars. These are the required LO powers for different type of mixers from world-leading manufacturers like ACST in Germany or VDI in the United States. And the blue bars show you basically, before we started our work, what was this LO power that could be reached by using a photodiode. And you see that in all cases the provided LO power is too low. So we could not use a photodiode to pump this LO or to pump this mixer. Now with the new high power photodiodes that we developed, you see this green, for example, this is for a subharmonic 300 gigahertz mixer. That means the LO frequency is only half, it's 150. And you see that at 150 gigahertz, we are above the required LO power for this mixer type. That means we can down convert a 300 gigahertz signal to a low IF frequency using one of our photodiodes and then have an optically coherent system. You see the conversion loss here on the right hand side. It's very flat over the IF band, and you see that we can cover here several gigahertz of bandwidth using this technology, and this is again an example for 10 milliamps. If you are comparing the performance parameters, you see ACST is the performance of the mixer as a pure electronic mixer when you use an electrical LO signal, and then the conversion loss is about 14 dB. If we use our approach, the conversion loss is slightly higher. It's 17 dB, but the advantage is that now we have a coherent system where transmitter and receiver are using the same optical signal to generate the terahertz signal and also to down convert it, which allows us to make much more efficient and more sensitive front ends. So that's the first step. Second step is, can we do it better? Yes, in principle. We are able to, or working on integrating everything. So in that previous example, the mixer was a commercial device. And our intention now is to integrate this mixing device with our photodiode in a single layer structure, so that we are fabricating the photodiode, but also the optical pump mixer ourselves using our own technologies. So we have two devices. Then one is the so-called FMBD. This is Fermi Level Managed Barrier Diode. This is the mixer that is using an optical input signal as the LO. And then the other device is the conventional photodiode that I showed you before. All of this is on a single layer structure. So we use one AP layer to the fabrication of both. That means we can now build an integrated circuit, a photonic integrated circuit that consists of photodiodes for the transmission and these FMBD mixers for the reception of the terahertz signal. Some details on this FMBD mixer. As I mentioned, this is a new device. To our knowledge, we are the only one who are fabricating this as a monolithically integrated solution. I'm not going into all the details, but what we currently do here in order to achieve the nonlinearity, we are not using a semiconductor metal interface as in a conventional mixer. In our case, we're using a hetero interface inside the layer structure. If you look at the left-hand picture, there is a hetero structure between the indium gallium arsenide layer and the INT layer. That is creating the barrier that we are requiring for the nonlinear, so for the mixing function. And then we pump it using the optically achieved or optically generated LO power from our photodiode. The advantage to do this is that now we are able to achieve much wider bandwidths as compared to conventional electronic mixers. And that's what you maybe can see on that slide. So this shows you the performance of this new type of optically pumped mixers. On the left-hand side, this is the most important figure here. You see the conversion loss in red, and you see the frequency on the x-axis. So you see the conversion loss is almost constant for a frequency range from 260 to 340 gigahertz. So now we are not talking about anymore about 10 gigahertz of bandwidth. Here we already have something like close to 100 gigahertz bandwidths. So we can think about having much wider spectrum that we can use for data communications using this technology. Everything is integrated, photonic integrated. So as I mentioned already, it's not only the mixer that can be fabricated on the same chip, but also the photodiode, and this is shown also on the right-hand picture here. You see the output power of one of the photodiodes fabricated from this chip as a function of the optical input power, or let's say as a function of the photocurrent. So both functions can be fabricated using the same epi layer structure. And both provide a huge bandwidth, which we can use for communications, as I will explain in the further slides. Okay, now we are changing a little bit the gears. We are now looking at the implementation of these technologies in communication systems. I will start with talking about fixed wireless access communications. This is systems where we have basically two antennas. They are looking at each other and they are communicating on a wireless channel. The frequency of this wireless channel can be varied. In our case, in this example, we are using a carrier channel of 300 gigahertz, so the antennas are radiating at a carrier frequency of 300 gigahertz. The system itself, the setup of the system is shown in the lower part of the slide. If you look in the middle, this is the wireless front end, and you again see what we have discussed at the beginning of the first slide. So we have the optical generation on the left-hand side, the laser and the modulator, which is then modulating the data onto the optical carrier. Then we use the second laser. This is located now in the wireless front end to generate the terahertz signal using our balanced photodiodes. In our case, in the wireless front end, we use two balanced photodiodes because we are using two orthogonal polarizations in the wireless domain to increase the capacity of the system. So we are sending on horizontal polarization, but in parallel also on vertical polarization, and we have different data on both of these polarizations. Then the wireless receiver, in this case at least, is a purely electrical one. We are using Schottky barrier diodes to down-convert the received horizontal polarization and the vertical polarization. Somebody is making noise here, sorry for that. Just a second. No way to stop them, too many. Okay, so I hope it's okay for you. So the horizontal polarization and the vertical polarization are both down converted to a baseband signal, and then we can analyze the data that we are receiving. Using this system, we have generated something like 100 gigabit per second, and we can wirelessly transmit this 100 gigabit per second to the wireless receiver. And as I mentioned already, carrier frequency here is 300 gigahertz. We use in this case 16 QAM modulation and a bandwidth of 12.5 gigabaud for this use case or for this system. So that was the first work. Continuing to some more recent work, this has been presented at the European Microwave Week in 23, and it has achieved Best Paper Award. It is basically the same system. It also uses optical modulation, and then we are generating the terahertz signal by adding another laser. This is exactly the same approach that I've been showing you on the first slide. So on the left here you see the two lasers. One is modulated, the other one is continuous wave. We mix the two lasers in the photodiode, we generate the terahertz signal, we radiate the terahertz signal to the receiver. In this work we use two different receiver types. The first one is the optical pump mixer. It's exactly what I've been showing you on the first slides, so the optical pump mixers. We also compared it to electrical mixers. This is the lower part where we use an electrical signal to pump the mixers and down convert the received terahertz signal. Using this system, we were now able to achieve 200 gigabit per second for a single beam at 300 gigahertz, and we were able to transmit this data over more than 50 meters. Just to give you an idea or a comparison figure, in the 5G systems or 5G mobile communications, if you use a full base stations, the total capacity of a full base station may go up to 10 gigabit per second. Here we are talking about 200 gigabit per second for just a single beam. We did a lot of comparisons. I'm not going into all the details here. We tested different modulation formats. So for those of you who are familiar with the modulation formats, you see that we use QPSK or 16 QAM, different type of modulations, and we tested different receiver architectures. In this example here, the solid lines is the electrical receiver, the dashed lines is the photonic receiver, and you see in that case we had a little lower signal to noise distortion ratio for the optical receiver, so the optical pump mixer. So in that case, the electrical pump mixer still was better than the optical one. Now I'm going to show you some other slides. We have improved the function of the optical pump mixers, and we can achieve even better performance now with the optical pump mixer. We also tested whether this could become a commercial product, and in order to make it a commercial product, we have to look whether we can be compliant to international standards. So we have to use exactly those frequency windows that are allocated by international regulation bodies for this type of communications. This shows you an example here. In this case, we are compliant to the IEEE 802.15.3D standard. So we are using transmission channels, frequency channels that are allocated by this standard for wireless communications. If you look at the right-hand figure first, you see that we are using the so-called channel number 66 and channel number 67. You see the frequency bands here for the wireless communications. The dashed lines basically show you the limitations that you need to keep if you want to be compliant to this standard, and you see that all our spectra are within this dashed line, so we are compliant to the IEEE standard. We again tested different architectures. We used single channel transmission, dual channel transmissions, different types of systems. In all cases, what you see here in the middle is the so-called error vector magnitude. You have to be below a certain figure in order to be sure that you can recover the data at the receiver. And for, let's say, some software-defined radio, we need to be better than 10 to the minus 2 bit error rate. This is the top line. And you see, in all cases, we are better than this. Even if we use more easy forward error correction, we can still transmit the data error-free. And we can reach here, in this experiment, we reach data rates up to 160 gigabit per second for this transmission, which is now IEEE compliant. And again, I want to highlight here, if you look at the system architecture on the receiver part, so this is the lower one, here we are now using the optical pump mixers to down convert the received terahertz signal to the IF band. So the top shows you the generation part, again the same story. We have a laser, we modulate the laser, we add the second laser, we generate the terahertz signal, we irradiate the terahertz signal, then it comes back to the lower part. And here we down convert it using these optical pump mixers. So we use our photodiodes to pump the mixer and then down convert it to the baseband and then analyze the data. And that can even be compliant to the standards. Okay, so we have built these systems for some use cases that I will show you at the end of my presentation. But of course, before we implement everything on a field trial or in a field trial, we also test the systems here in our department. You see a picture of our department here. I'm going to show you a short video which shows you the implementation of this fixed wireless access system in our labs. Actually, we are radiating between our department and the Fraunhofer department. I start the video. So this is fixed wireless access tests on the campus. The top building here, or the front building, is Fraunhofer, and now we are seeing again the top of, or the rooftop of our building, where we have located one of these antennas that are radiating to the other building, which is some 150 meters apart. And we can transmit much higher data rates. In this case, we use the electronic system that we used here, only supported up to 2 gigabit per second, but enough for our use case. The front ends can do much more, as you have seen, but the data signal here is 2 gigabit. And what we want to use it for, and I just stopped the video here for a short second, we are basically using it for scanning trains. So what you see here is that we are sending real-time pictures from scanned trains. So we are scanning trains from both sides and from the top. And that needs to, this data, this video data, has to be sent to a remote central unit, uncompressed. So we need a high data rate and we need a fast link in order to transmit this data from one place to another. At the end of my talk, I will show you the implementation of all these systems in an industrial field trial, and then we will come back to the system that then has been installed in an industrial field trial. But for the moment, at least, this shows you that the system is operating. Here we are using it for transmitting several video streams in parallel. Okay, let's say switching gears again. Now we saw fixed wireless access. This is point to point. The antennas are fixed. They are communicating to each other, but they cannot move. So what happens if one of the antennas want to move, or if one of the antennas is a human being that is moving in front of the antennas? Then we need to have some mobile communications. And as maybe I didn't mention, but maybe you have seen that from the video, the antennas that we are using are highly directive. So in comparison, or let's say in difference to the mobile communications, we are using directive beams. And if one of the antennas, or even both, are mobile, we have to steer the beam. And that is done by optical technologies. We have developed different photonic integrated ICs to support this beam steering. This shows you one of the chips, which is using a silicon nitride technology in this case. It contains a number of phase shifters and true time delays. So we are able to delay the signal of the data to the individual photodiodes. We have basically a phase array at the output of this chip, so an array of photodiodes with antennas, and we can delay the time at which the data signal arrives at one of the photodiodes, and that allows us to steer the beam. So in this example, you see that now the wave front is no more perpendicular to the antenna array, to the phase array, but now we have an angle here because we have delayed one or all these channels in a way that it now steers the beam into a certain direction. You see the result here. This is basically the phase shift that is required altogether to do this beam steering. We need a phase shift of 360 degrees, and that is what we can achieve by changing the operating conditions of these ring resonators here. So you see the blue and the red line show you that we can reach a 360 degree phase shift using the control signals for these ring resonators. This is all integrated. It's a small tiny chip. So it's only some photonic chip with fiber in, fiber out in order to be able to steer, or let's say delay each channel here independently. There are other solutions. Very complicated slide, I know. I will try to explain it to you in easy words. So here we are using special antennas. It's antenna arrays again that also allow us to steer the beam with another degree of freedom. Here we can also steer the beam by using a different carrier frequency. So we are maybe not using only 300 gigahertz, but maybe 310 or 320. And depending on the carrier frequencies, the antenna will radiate the beam into a different direction. You may see that from the figures in the middle here. You see for different frequencies, you see different directions. You see the plot here shows you in which direction the antenna is radiating. So for the frequency in the middle of about 273 gigahertz, you see that the radiation is almost perpendicular to the antenna, and that means we are radiating here front end, and then we can also steer the beam to backfire and front fire by changing the frequency. This is a very tiny chip because we are using high frequencies. Everything can be very small. You see the small chip next to the euro coin here, and actually it's only the lower part of the chip, which is the antenna. So it's a very tiny chip that can be used in order to steer the terahertz beam. So we can enable mobile communications using this technology. We have integrated several of these antennas in parallel and also integrated another freedom to steer the beam. This now allows us to steer the beam not only in one direction, in elevation, but also in azimuth. So we are now able to steer the terahertz beam in both directions. And we have tested and measured this. And what you see here on the slide is the beam angle that we can steer. So in both polarizations, green is azimuth and red is elevation, we can steer the beam from about -20 to +20 for azimuth and -10 to almost +40 in elevation. So in both cases, something like 40-45 degrees of beam steering, but two-dimensional. We can steer in azimuth and in elevation independently, and that allows us to do 2D beam steering. Now we simply have to add data onto the terahertz signal and then send the data into different directions. This is what we did. In this case, we used the QPSK modulation. You see the constellation diagrams here in different angles and different directions. And in all cases, for all angles, we are able to detect the data signal here without any problems. You see clear constellation diagrams in all directions. Well, this can be further, let's say, integrated. So now we have everything integrated. This is the idea. The beam forming chip, this is OBFM chip. Then some amplifiers like optical amplifiers, the photodiode array, the antennas, and there has been a lot of work in integrating this with electrical amplifiers. I'm not going into the details here, but at the end it allows you to generate multiple beams that you can steer independently and transmit high data rates to remote receivers. And in that use case, or in this example, we did this here for 2 beams, and we were able to reach a couple of 10 gigabit per second for each of the individual channels. So the total capacity of the system, of course, is much higher because we can use multiple beams. As I mentioned in this test, we did it only for 2 beams, and we were able to carry up to 30 gigabit per second on a single beam in this with this technology. This is further explained in this next coming up video. So again, it shows you a little bit of explanation how we are using this frequency steerable antenna. It's called leaky wave antenna. Just have a look.
Using leaky wave antennas, beam steering is simply accomplished by sweeping the operating frequency without any complex feeding control circuits. Indium phosphide substrate is used for future monolithic integration of the antenna with electric or photonic terahertz sources and receivers. The beam direction changes by sweeping the RF frequency, as can be seen in the animation. Realized antenna gain with a lens is 18 dBi. Terahertz signals are generated by a photodiode and fed to the antenna using a GSG probe. The receiver is installed on a goniometer to detect terahertz radiation from the antenna at different angles. At 280 GHz, the radiation angle is 6 degrees. The Keysight digital signal analyzer is used for high-frequency measurements and shows the received RF signal in time domain. It comprises a Zadoff-Chu sequence for channel estimation, highlighted in red, and 2 data symbols, here highlighted in the green box. The green box shows the actual laser parameters. These windows allow you to adjust the main parameters of the optical systems. The other windows allow you to analyze the received signal. In the yellow box, the data spectrum is shown. The red box visualizes the frequency selective behavior of the transmission channel, while within the purple box, the received constellation diagrams and measured SNR are shown. As the beat frequency of both lasers defines the RF signal, turning of one laser wavelength results in a changed RF. In combination with the steering behavior of the leaky wave antenna, a signal loss at a fixed receiver position is observed. Since the RF signal was changed from 280 GHz to 320 GHz, no signal can be detected at the former angle. It confirms the beam steering capabilities of the leaky wave antenna. Due to the frequency change, the antenna beam now points at an angle of 34 degrees. After adjusting the terahertz receiver to the new transmission angle, the data signal can be detected again and shows the same performance as before. For all angles, a minimum data rate of 24 gigabits per second is achieved using QPSK modulation and a bandwidth of 12 gigahertz. Also, higher order modulation is possible. Using 16 QAM, the maximum data rate is 20 gigabits per second for all angles. Without further amplification, the maximum transmission distance is about 30 centimeters. This can be further extended to more than 60 centimeters by using additional lenses. Applications of the developed terahertz antenna chips include beyond 5G wireless communications, terahertz imaging, and high-precision radars.
Basically, what it showed here is the function of this frequency-dependent steering. And we are able then, by changing the wavelengths of one of the lasers, we are changing the frequency, and this changes basically the direction in which the antenna signal is then radiated. Okay, another application using a similar technology for satellite communications. The purpose here is a little bit different. It's not just the high bandwidth and a high data rate. This is what we already have seen for fixed wireless. And for mobile communications, there we are using a high bandwidth in order to have a high data rate. Here we are using the same approach, but we want to replace the copper cables using fiber or let's say mainly in order to reduce the weight. This is work that we were doing for Airbus. In this case, you see one of these communication satellites, but also Earth observation satellites have the same structure. So they have quite long antennas, and they are consisting hundreds of antennas. Each of the antenna element on these panels have to be locked, or let's say linked, by an RF cable to the core of the satellite, and that is a huge and heavy harness. You see in the inside here the harness. It is very heavy and very cumbersome, and the intention here is to get rid of this by using photonic technologies. I will show you in a few seconds. First of all, another application. This is using the same technology. We call it radio over fiber or radio frequency over fiber, RFOF. We can also use the same technology to backhaul base stations, for example, in the train, where we have fiber next to the track, and then we are radiating the backhaul data using an antenna into the train, and then the base station travels with the train. So you don't need to have base stations all along the track. You just have a base station in the train, and you just communicate from this remote unit into the train, but just the backhaul data using RFOF technology. This is one of the developed modules that we were developing in collaboration with some companies, as you can see. And it's a very tiny product here, and it basically consists of a couple of channels. So this module allows you to send RF data, actually 4 channels of RF data independently over this multi-terminal fiber. So RF goes in and it's transmitted over fiber, and at the other module, it's converted back to RF. So no more cables in between, just lightweight and flexible fiber is used for multiple channels in this application. The modules itself contain electro-absorptive modulated lasers for the transmitter, and in the receivers we have photodiodes integrated with transimpedance amplifiers. Another application, now again we are focusing on bandwidth, but even wider than we talked about before. Before we had one waveguide band, so something like 100 gigahertz in the WR3 range. Now we are looking at something which has a much wider multi-octave or terahertz bandwidth. This shows you one of the fabricated modules here. It is using a photodiode, and now we are transmitting the generated terahertz signal not anymore in the hollow waveguide, but in the dielectric silicon waveguide. You see this needle that looks out of the waveguide here. The terahertz wave is now guided inside the silicon, and that allows us to cover huge bandwidths. you see a measurement of this module from 100 to 600 gigahertz. So, and this measurement already shows the bandwidth of 500 gigahertz for this technology, and it can be further increased. This is really huge, and nothing else compares with this technology. We can use it for different applications. For example, we can use it for optical VNAs. VNA stands for Vector Network Analyzer, and I guess most of you will know it. Usually it's an electrical device fabricated by one of these test and measurement companies. Now we are using an optical technology. We are generating the frequency here by our technology. Then we are testing, for example, in this case, we tested different waveguides. We just had a look what is the lower cutoff frequency of different waveguides. We also tested filters fabricated by our collaboration partner, Rohde und Schwarz. So we used basically the component as a transmitter for an optical VNA, and we were able to measure any component in the frequency range between 100 and 600 gigahertz. We can also use it for imaging. Some examples here show you we are generating a high frequency signal that allows us, because we have a small wavelength, a high resolution, spatial resolution, and you see some examples here where we have an image in the terahertz domain of a 1 cent coin or a leaf. And the last example, also very critical for many applications. We are using a technology which is called photonic microrings. The heart of this technology is this greenish chip here. You see in the upper right, you see the chip as a manufacturer chip. It basically consists on a ring resonator, and what it does is it is introduced by a CW laser. So we use a laser with a constant frequency, and this chip, because of nonlinearities that we use in the material, generates an optical comb. So it generates a spectrum of optical lines that you see here in this picture, from red to purple or blue, and the difference frequency between all the lines is very, very stable. It is defined by this chip, and that allows us to generate a very low line width, a very low phase noise signal that is necessary for time synchronization in almost all electrical applications. You see this here on the left hand side. You see this generated optical comb with a huge number of lines. And as I mentioned, the difference frequency between the lines is very stable. It depends on the ring resonator, the KR microring chip that we fabricated. This is one resolution or one solution for 318 gigahertz. Now we have high frequency photodiodes, our own photodiodes. We can use our own photodiodes to generate then the 318 gigahertz signal, and we can measure the phase noise of this terahertz signal by down converting it to a lower frequency. And that's what you see on the right hand side. And what is important here, this is a very low cost free running chip, and if you look at the far from offset, so this is at 10 to 6, 10 to 7 hertz offset frequency, and the lower black line shows you, to our knowledge, the best existing electrical synthesizer on the market from Rohde Schwarz, SMAB B711, and you see at the high offset frequencies we are already reaching this performance, although we just use a single chip to generate this signal. So it has a very low phase noise. At the lower cutoff frequencies or lower offset frequencies, you see a higher phase noise. This is because we have not yet implemented a PLL, which is the next step in order to also reduce the carrier or the phase noise at the close to the carrier offset, so at lower offset frequencies. But again, at the high offset frequencies, we already reach the performance of, let's say, world-leading instrumentations on the market. Okay, so this brings me to the end. I will now show you one more video, or let's say two more videos, to show everything together working in an industrial environment. Here the industrial environment is our port in Duisburg. It's the largest inland port in the world, and the point here is that they want to increase the capacity of their ports. They have a couple of lock ports in the city, altogether 6, and there is no more room to build new lock ports, so they have to increase the capacity by having a better use of the existing area. That's why they want to speed up the loading and dropping from the containers from trucks or from trains. And in order to implement that, we have to enable the crane to be operated automatically. We had to install LiDAR systems or LiDAR systems to survey the environment in order to avoid any accidents. But we also had to install new mobile systems, so we have increased the capacity using, let's say, kind of virtual campus network developed by Deutsche Telekom. And then we have installed a fixed wireless access system that you saw in order to scan the train when it arrives in the port and send the data to the terminal operating system. This is the TOS here in the middle. So the scanned data, the scanned video data is immediately sent uncompressed to the TOS. So the TOS knows what train is coming, where are the containers, which numbers are at which position on the track or on the train. And then the final step that we need to do is to develop a radar system, because the trains stop somewhere in the port and we need to know exactly the position of the train in order to calculate the position of the containers and then tell the train at which position he can pick up the container and where to drop the container. This is the full system that has been developed. Now, first a video, quick video. I hope you can hear the sound. No, there is no sound. I will explain it to you. So this is the radar system that measures the distance from the end of the track to the train. We have installed a couple of things here, 5G routers. We are locating it by GPS. There is a visual camera, there's a radar system. It operates at high millimeter wave frequencies. Inside there's lots of electronics that is necessary in order to calculate the data. Some switches, a Raspberry Pi is used for the digital signal processing here. All of this is the radar module here that looks out of the box, and this shows you the scenario. So the train is coming, the end of the track is located by GPS, so we know exactly where the radar is located, and then we measure the reflections that we see from the environment. And you see there's lots of reflections to the left and to the right, and they are only caused by trucks driving along the tracks here. So there is no train, but you see if you look at the cloud, at the point cloud here, you already see some reflections to the left and to the right that are created by the trucks. But now the train is coming, and if you look at the picture, you see the point cloud, which shows you basically the distance of the train to the end of the system or to the end of the track. There is another example where we have another train coming, and you see here in this increased picture that we can precisely measure the position of the train. And that means we can now calculate, because we measured the container when they arrived in the port, we can measure the location of each container and tell the crane exactly where to put and where to pick up the container and where to drop the container using this information. And then this is the final video here, which shows you everything in operation.
Wir sind heute hier am Duisburger Hafen und hier werden jährlich fast 60 Millionen Tonnen Güter aus aller Welt umgeschlagen, auf Schiffen, auf Zügen, auf LKWs. Und das ist übrigens mehr als an jedem anderen Binnenhafen in Europa. Und dank 5G sollen hier in Zukunft sogar noch mehr Container verladen werden. Wie das funktionieren soll, das zeigen wir euch heute. Auf dem Hafengelände an der Mündung der Ruhr in den Rhein entsteht ein riesiges 5G-Testfeld. Dazu wird die Telekom Teile des Areals Lokport 1 in Duisburg-Rheinhausen mit 5G versorgen. Das Gelände umfasst eine Fläche von 265 Hektar und ist damit so groß wie 370 Fußballfelder. Gemeinsam mit weiteren Projektpartnern werden die Uni Duisburg-Essen und die Duisburger Hafen AG hier im Projekt 5G Smart Lokport neue Logistiklösungen auf Basis von 5G entwickeln und testen. Eine wichtige Rolle spielen dabei intelligent vernetzte Containerkräne.
Was wir jetzt hier im Hafen uns speziell anschauen wollen, ist die Digitalisierung aller Einheiten des Hafens, die für eine teilautomatische Kranfahrt erforderlich sind. Wir haben hier Dinge wie zum Beispiel Terminal Operating System, Kranmanagementsystem, jede Menge Züge, wir haben hier LKWs und wir müssen diese Einheiten im Prinzip digital erfassen, wenn wir in der Lage sein wollen, zukünftig teilweise diese Kranfahrt zu automatisieren.
Warum braucht es 5G dafür?
Um einen Kran automatisch fahren zu lassen, müssen wir die Umfeldüberwachung hier im Prinzip extrem aufrüsten. Das heißt, wir müssen sehr viele Kameras hier in die Nähe des Krans bringen, der die gesamte Umgebung hier im Prinzip analysiert. Hier fahren LKWs, hier fahren Züge, hier laufen Menschen. Und diese Datenraten, die wir damit ins Netz streamen, können wir nur mit 5G. Also nur die 5G-Zelle bietet genug Kapazität, um diese Daten auch in die Zelle zu streamen.
5G ist aber nicht nur für Containerkräne wichtig, es hilft auch anderen Unternehmen, die hier am größten Binnenhafen Europas tätig sind.
5G bietet eben für die Unternehmen im Duisburger Hafen die Möglichkeit, neue Anwendungen im Bereich Logistik und Supply Chain auch zu erproben. Wir haben das Problem, dass wir heute als Hafen begrenzt sind im Wachstum. Wir bekommen nicht neue Flächen, wir müssen eben schauen, dass wir die bestehende Infrastruktur besser auslasten.
Und sag mal, man denkt jetzt nur an Schiffe, wenn man an den Hafen denkt, aber es gibt ja nicht nur Schiffe hier. Ne?
Genau, also der Hafen, man denkt nur an Schiffe, genau richtig, aber der Hafen ist mehr als die Schiffe. Es sind 20.000 Schiffe, die den Hafen jährlich ansteuern. Viel wichtiger ist aber eigentlich sogar der Bahnumschlag im Hafen. Also wir haben natürlich auch viele Züge, 25.000 Züge pro Jahr, die hier abgefertigt werden. Und das wiederum muss natürlich synchronisiert werden auch mit den LKWs, die den Hafen ansteuern, die beispielsweise in den Hafen kommen, um Container auf der letzten Meile zuzustellen. Also wir haben hier 3 Verkehrsträger, die miteinander synchronisiert werden müssen und das macht halt auch eine große Komplexität aus.
Kann Duisburg ein Vorbild für andere Häfen in Deutschland und darüber hinaus sein?
Ja, definitiv. Also das Thema Teilautomatisierung in Containerhäfen, das ist einmalig. Also das gibt es in keinen anderen Binnenhäfen. In Seehäfen wird sowas schon erprobt, teilweise mit anderer Technologie tatsächlich. Aber in Binnenhäfen ist das einmalig und das kann tatsächlich ein Vorreiter sein für andere Häfen auch und kann auch übertragen werden natürlich auf andere Häfen.
Damit all die Innovationen hier laufen, stellen wir hier ein 5G-Campusnetz bereit. Das ist ein lokal begrenztes Mobilfunknetz, das die besonderen Erfordernisse des Hafens erfüllt.
Wir haben hier unser öffentliches Mobilfunknetz genutzt und auf diesem öffentlichen Mobilfunknetz bauen wir einen sogenannten Campus M. Wir bieten dem Kunden eine besondere Qualität, sodass er sozusagen abgeschirmt seine Daten verwenden kann, um diese Industrieanwendungen, die wir jetzt hier im Hintergrund sehen, auch wirklich nutzen zu können.
Und erklär noch mal technisch, was sind denn die Vorteile von 5G im Allgemeinen und jetzt hier speziell am Hafen?
Technisch gibt es viele Vorteile von 5G, die über mehr Bandbreite hinausgehen. Mehr Bandbreite gibt es auch, gute Nachricht, ist für uns alle wichtig. Aber es gibt auch viele Vorteile, wo man aus dem Netz heraus zum Beispiel eine Reaktionszeit, es ist so ein bisschen wie ein Reflex bei uns selber. Wann reagierst du, wenn man dich anfasst oder so? Die Latenzzeit des Netzes ist deutlich geringer geworden bei 5G und man kann sie nunmehr auch noch steuern. Es gibt noch andere Sachen wie zum Beispiel Ortung. Also wo befindet sich konkret ein Container? Das kann man im 5G-Netz nachvollziehen. Im Endeffekt geht es ja darum, vielfach Daten zusammenzubringen, um diese auswerten zu können, um dann mit diesen Daten das Geschäft besser steuern zu können. Im Endeffekt, gerade bei Logistik, geht es hauptsächlich um Effizienz.
Also 5G liefert hier ordentlich Netzkapazität für all die Anwendungen am Hafen, wie zum Beispiel die teilautomatisierten Kräne. So können dank 5G hier in Zukunft noch mehr Schiffe ihre Anker setzen. Wir halten euch natürlich über das Projekt auf dem Laufenden, aber schreibt uns...
We stop it here. Okay, so this brings me to my final conclusion slide. So I've shown you some of the key functions or key components that are required to build these photonic front ends operating in frequency ranges. All the examples I've showed today from 30 gigahertz all the way up to 600, 700 gigahertz. And I've also showed you some of the potential use cases and some of the demonstrations. Sometimes it's demonstrations in the laboratories. Sometimes we can at least demonstrate already some systems and even field trials for the automation. The applications I showed you were fixed wireless communications, so point-to-point communications, mobile communications. We have technology for satellite communications and Earth observation. We also had a look at the performance of an optical VNA that is using photonic technologies for an ultra-wideband spectroscopy system here. Imaging, we also looked at these imaging systems for imaging coins or leaves or some other things. And finally, we had the field trial where I've shown you some of the use cases for radar and then also an automation here in the example of this crane that is operated at Duisburg Port. This is the end of my presentation. Thank you for attending and I'm looking forward to your questions if you have any.
Thank you, everyone. And thank you, Professor Stöhr. You're welcome to send in any questions you have. We have a couple of questions received beforehand. For anybody that was a little late to the call, can you tell us what the unique selling points and major use cases for Terahertz technology for communications are? And how do these compare to optical and radar approaches?
Mm-hmm. Well, I think I at the beginning of my presentation, I have shown some of the generic, let's say, advantages of using Terahertz and especially of using photonics. If you want, we can also have a look at this slide. So I'm sharing my screen again. So in short, I mean, the Terahertz opens up huge bandwidths. We have seen some of the technologies that can basically reach this. So we are able to generate huge bandwidths, and huge bandwidths means we can have a very high data rate. So the capacity that we can send over fiber, I've shown you some of the applications were even up to 200 gigabit per second for single links. But we think in the future we can even have much higher data rates on a single wireless beam. So we can send data rates like in the fiber using a wireless channel. So terahertz is very important because it offers a huge bandwidth. That's the key, basically key advantage for communications. There are other advantages like low loss, but this is only if we use fiber. So if we use a photonic terahertz front end, then we are transmitting the terahertz signal over fiber, and that is very low loss. There is also low EMI. We can place different optical channels very close to each other and they will not disturb themselves because we have a low EMI. This is in contrast again to electronic systems where you cannot place different channels closely to each other. So those are, besides low weight, those are the key advantages for communications. Bandwidth is maybe the most important one. High frequency, which means that we may be transparent to some materials like closest, allows us to do imaging after or in a box. We can look into a box, so we can look behind closest at the airport. But this is not so much of importance for communications. Small wavelengths is another feature of terahertz. Of course, it's smaller compared to microwaves, and it allows us to do imaging at a much higher resolution. But again, the later two, the generic advantages are not that important for communications.
Thank you, Professor Stöhr, for the overview of where terahertz technology stands in relation to other approaches. I believe you touched on this briefly, but could you elaborate on specific advantages that photonics offer over purely electronic approaches in terahertz communications?
Yeah, I mean, I just addressed some of these aspects here. One, of course, was what I mentioned, the low loss fiber. I can give you some quantitative numbers if you want. So the loss of an optical fiber, it's independent whether you are transmitting an RF signal at the microwave frequency range or terahertz or purely optical. So the loss of an optical fiber at the wavelengths of 1.5 micron is about 0.1 to 0.2 dB per kilometer. So after, let's say it's 0.2, then after 15 kilometer, we have lost only half the power. If you use a very expensive RF cable, even for lower frequencies, I should say that there is no RF cable for terahertz on top of it. But even if you go to lower frequencies, like for example 30 gigahertz, then the loss of an RF cable is higher than 3 to 4 dB per meter. So in a cable, although you're working at much lower frequencies, you lose half of the power already after 1 meter. So of course it makes sense to use the fiber as a transmission media to transmit the data signal to remote antennas. But of course this requires the implementation of photonic front ends. And that's maybe the key advantage is this low loss feature of the optical fiber. Another feature that is maybe not so obvious if you look at this example of this wireless communication system is the low weight of the fiber. But I mentioned already in my presentation the application of using fiber or RF over fiber technology in satellites, for example. And there, the weight of the harness, of the cable harness, is really crucial. It's critical. It's not just cumbersome, but it's also heavy, which is costing a lot of money in order to launch the satellite. Replacing all this cable harness by an optical fiber would save a lot of money because it would save a lot of weight. So it always depends a little bit on the application. What I should mention here also in terms of, if you compare it to electronics, the photonic systems offer a much wider bandwidth. So the bandwidth that we can provide on the transmitter side and also on the receiver side is much larger, much wider than compared to pure electronic systems. So if you want to go to the extreme high data rates, then you need this technology because it's the only one that can provide you sufficient bandwidth.
Wow, it's really clear that photonic integration could be a key enabler in this space. Moving beyond technological potential, I'd love to hear more about what's actually happening in practice today. You mentioned regulation and standardization earlier. So could you update us on the current status for millimeter wave and terahertz frequency bands?
Yeah, that's a good question. I mentioned it in my presentation. Let me go to a slide that I didn't show during my presentation. I hope you can see the slide here. So first of all, when we talk about communications, we have to differentiate between these fixed wireless access systems, so point-to-point, and mobile systems that are usually operating at much lower frequencies. So for example, 5G systems are nowadays operating mostly around 3.5 or 3.6 gigahertz, whereas fixed wireless access systems are already using frequencies like 70 or 80 gigahertz for commercial products. So what I mentioned during my presentation is that there are two major regulation bodies in the United States and also in Europe that are currently regulating higher frequencies for communications. It is not necessarily defined whether mobile or fixed, but at least they are opening these frequency bands for communications. And here we are talking about the frequency bands that you can see here on the slides. They are in the W band, this is the 92 to 114 gigahertz range, in the D band, which is 130 to 175 gigahertz approximately, and in the WR3 band, this is most examples that I showed today, which is around the 300 gigahertz, a little bit lower than 300 gigahertz frequency range. And the difference here, why are they regulating these frequencies, is you see the widths of the channels. If you look at the 300 gigahertz as an example, you have this pink channel that has a bandwidth which is allocated to communications of several 10 gigahertz. In the microwave region, you only have a bandwidth of a few hundred megahertz, if at all, or if not even smaller. So you have to compare very small bandwidths to bandwidths of a few 10 gigahertz per second. And of course, this allows you much higher data rates. So regulation is already taking care about it. And there is also one standard already existing from IEEE for the transmission of 100 gigabit wireless signals using these kind of channels. But still, of course, national regulation bodies have to accommodate these frequencies. So you have to double check for the time being whether you are allowed, in which country you are, to use this frequency for wireless communications. So internationally, there are regulations and there is also a standard, and there is more to come also in the mobile communications. But again, also the national organizations, governmental regulation bodies have to agree on these frequency ranges. So it may be able to use it. For example, you can use 70, 80, and even 90 gigahertz already in most of the countries for fixed wireless access. And in the future, I think we will also see higher frequencies that can be used then for communications. So there's a clear roadmap to open up these higher frequencies also for commercial applications.
And to wrap things up, we received a question from the audience about the short and long-term outlook. What do you see as the main opportunities and challenges for terahertz communication technologies in both the near term and the longer term?
First of all, answering from a system point of view, more short term, I would say, is the fixed wireless access systems. Here we already reached some maturity. Components are more or less readily available. The photodiodes that I showed for the generation of these high frequencies, currently there are not so many suppliers worldwide. I think we are the only one in Europe There is another supplier in Japan, and also some work is underway in China and in the United States. But there are already some of these components available. Also amplifiers, antennas, this is all available. So it is possible to set up a fixed wireless access system operating at W-band, D-band, or WR3 band. I would say in a short term. I mean, to set it up, it's already done. We can set it up. We have it running here. But to make it a commercial product, it will still take a little bit of time. But I think this is still short term. For mobile communications, as I mentioned, we need some technologies to steer the beam. We have invented photonic technologies, photonic integrated circuits, photonic ICs to do this beam steering. And we can demonstrate, at least in the labs, that we are able to steer the beam and transmit several tens of gigabits of data for each of the beams. But this is still short range, and it's mostly lab-based demonstrations. We have already done a little bit of outdoor demonstrations already for some longer distances using similar technologies like this leaky wave antenna that I've showed you in the video. But I would say in terms of applications, this is more long-term. So more short-term is fixed wireless, more long-term is the mobile communications. And in terms, if we want to answer this question from the technological point of view, there is a lot of work still to do in the integration. Not only the photonic integration, I've showed you some examples of photonic integrated circuits or photonic ICs, like this integrated chip for beamforming. But if we want to have everything integrated in photonics, we need different semiconductor structures. A laser is usually made of indium phosphide, and this very low loss beam steering chip is made from silicon nitride or sometimes lithium niobate on silicon photonics. So we have different semiconductor technologies, and that means we need a hybrid integration from an indium phosphide laser chip to this silicon nitride beamformer chip to the photodiode chips, which are again on indium phosphide. And this still creates a couple of challenges here. We are working on this to have a hybrid integrated photonic ICs. You already mentioned this new workshop series here, or this workshop on photonic ICs, the upcoming workshop here. So we are working on it, but it's still a technological challenge. And on top of it, we also have to work on the integration with electronics. Again, we are doing this already with some partners. So as an example, we may need higher power. We want to have a photodiode integrated with a Terahertz amplifier, for example. And we have already demonstrated that this can be done by some interesting technologies that are able to interconnect, let's say, Terahertz devices with low loss. But there is still some work to do. So also photonic electronic integration still needs to be improved in order to increase the maturity of the technologies of the chips for future applications. Like, for example, imaging, spectroscopy. I showed you the optical VNA, or for the timing synchronization, or for radar examples. We are working with industry to develop Terahertz radars using these technologies. But this, I would say, is more long-term.